Okay. Recognize the problems that lead to indifferentiability. Sometimes people will say this things are undifferentiable or indifferentiable. Anyway, same thing. So what sort of problems lead to that? This is all going to be 17G plus there'll be some stuff on compass, a bunch of, how well is that coming out? There you go, a bunch of curves just like that. For this stuff, the curve thing, you're just drawing very rough derivatives over the top of those, or you can draw them on a separate bit, that's all well and good. So that's what the worksheet is, and then 7G is this sort of stuff. It all combines pretty nicely. We're just touching on some annoying things that can turn up. So when are they differentiable? When a function's differentiable? Well, here's the proper definition. If at some value for x, the first principle exists, or the limit of the first principle exists, then the function is differentiable at that point. Brilliant, that's a whole lot of technical jargon. We're going to step that back a little bit and just say it's differentiable if it is continuous and smooth. Now, what do I mean by all that? Well, let's have some lovely examples to get there. Okie dokie, so I've got this hybrid function. Okay, well, everywhere along this nice straight line, so everywhere along x up until -1, that's all just a nice function x. We know that we can derive basic functions like that. The gradient here is always 1, so it's definitely differentiable. Cool, what about this section here? Well, all of there, that's a nice flat line, y equals -1, so the derivative is 0 there, because it's just flat there. Here, similar story, it's a +1, but the derivative's still just 0, because it's flat. And out here, our derivative is 2x, so because it was x squared, derivative of that, 2x. So that's all well and good. It's changing as we go, but that's fine, we can still get an expression for it. The fiddly bits come from these guys. So if I consider what a derivative is, one way of thinking about it is tangent lines can exist there. So here I can draw those green lines on top of this, and it's totally fine. You can think of that as a tangent to every point on the line, just the tangent to a straight line is itself. So it's a little bit weird. The tangents to this, that's fine. I can draw a whole lot of little tangents, bang, 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 and all of those are perfectly fine. Where I get into trouble is lines like this. Well, I could draw a tangent that way, as with this, but I could also justifiably say, oh, actually, it's going flat here, so maybe the tangent actually goes that way. And then potentially I could even be justified saying, oh, it's just at this point that I'm interested in, so maybe it's somewhere in between. So we're having a disagreement. Whenever you have a disagreement like that, you know that something's wrong. So we are not differentiable at x equals -1. Next part. We go, well, here, my line doesn't even exist. But as I approach that, I could say I've got a derivative of 0 approaching it this way, and I could say I've got a derivative of 0 approaching that way. But if I think about the tangent argument, I could say that, oh, it's going dead straight, but I could just as easily, for this non-existent point, say, oh, the derivative is that way, or something in between. So I'm getting disagreements, so that's where we're going to get problems. Similar story, I could say this is going dead flat, but I could say it's going vertical or diagonal or anything, because to that infinitesimal point, I could draw tangents all the way around it, and all of them are still tangent. So that's no good to me. What about this guy? Well, it looks like this part is going dead flat, looks like this part's coming down a bit, and again, I could argue anywhere in between just as easily. So x equals 0, that's problematic, and x equals 1, +1 is all problematic. So for this connection, we were continuous because at no point did the line cease to exist, but it's not a smooth transition from x to -1. And since it's not smooth, we can't differentiate at that point. We can differentiate before it, that's fine. We can differentiate between x is -1 and x is 0. We can differentiate between x is 0 and x is 1, and we can differentiate after 1, but at exactly these values, we can't differentiate because it doesn't have any meaning at that point. So here we've got problems with smoothness. Here we've got problems with continuity because we just suddenly teleport. Well, how much of a change was that? Well, it's an infinite amount of, it's a change of 2 over a distance of 0. So we've got 2 divided by 0. What kind of change is that? That's undefined. So we've got problems defining that that derivative. And here we've got continuity, but again, we don't have smoothness because it's all of a sudden just jerked up. Cool. Well, what about something a bit more straightforward? Well, here I could draw a whole lot of tangents. Yeah, that's fine, that's fine, that's fine, that's fine. But when I get to this endpoint, we take a look at it and go, hang on, I could justify it going maybe this way, but it seems like I could draw a tangent that way, or a whole bunch of options. So this guy is differentiable from above 0, but once we hit 0, we can get as close as we want. But when we actually hit 0, even though the line does exist there, it's not existing anywhere to the left of that, and so we have this real problem of trying to decide where the tangent is. Also, the graph doesn't even exist over in the negative parts for x, so we can't get any meaningful derivatives over here either. Okay, well, what about something like 1 over x? Again, you can go to your tangent line thinking. Here we're going this way, this way, this way, this way, this way. Here we're going this way, this way, this way, this way. Okay. Well, these are all fine. This will just go on forever. It'll get closer and closer to 0, and it'll go off to infinity. That's fine. Same story on this side. Here we're getting more and more negative, and this gradient is approaching negative infinity. Well, if I go up this way, the gradient's also approaching negative infinity. So it seems like we've got some sort of smoothness going on, but we are most certainly not continuous. We're suddenly jumping from negative infinity up to positive infinity. So we've got a problem. So x equals 0 is not differentiable for this function. Oh, I didn't write it over here. So whenever x is less than or equal to 0, this won't be differentiable. Cool, over here, everything except for 0 is fine. Brilliant. What about something like this? This looks a little bit weird, but we can go, oh, okay, well, isn't that just this? In which case, we get a line like that. Almost. There's a slight thing that we've got to be a little bit careful about. When I did this, I assumed that x was not 0. Because if I put 0 into that, I get 0 over 0, undefined. I get problems. And the way we represent that is with a nice hollow. Cool. Okay, can I draw tangents to this? Well, a straight line, its tangent is itself, so that's fine, 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 fine. Everywhere up here is fine. Blah, blah, blah. But when I'm exactly at 0, I've got a problem because I could potentially draw maybe a tangent that way, because I could go through it, and then that's kind of tangent to both those lines, sort of. If you start looking at this on an infinitesimal scale, you can zoom into that as many times as you want, and there's always going to be this gap just in the middle, so it's not actually continuous. It's super, super, super close, but not quite continuous. And so if it's not continuous, then at that point of discontinuity, can't be differentiated, at least not meaningfully. Cool, so that's fine everywhere except for 0 as well. What about something like this? All right, well, let's figure out what's going on. It looks like we could draw some curves all through this, but what happens at these points? All right, we'll have to do some calculation. We shall do this in Poiple, because I can. Okay, we'll look at each of these parts as we go through. So they transition at -1 and +1. So derivative of this, so this part, I'm just going to do this arrow, I'm going to say means derive this part. In fact, we'll do this in purple there. So the derivative of that, hopefully, very obviously, is -2. Cool, when x is -1, it's still -2. That's fine. What about this guy? When he derives, I get 2x. So at x equals -1, I get, oh, actually, better yet, rather than writing it like that, I get, so when x is -1, my derivative is -2. Okay, for this one, doesn't matter what x is, so even at x is -1, I still get -2. Hopefully we can see these are pretty obviously in agreement. Great, so that means that they're smooth, because my derivative is the same at that transition point. Okay, fine. Do they equal the same value? Well, over here we can say, well, this point is from the purple side, which is this one. As x approaches -1, this thing approaches +1. Okay, what about this guy? As x approaches -1, this whole thing goes to +1. So they agree on that point. They also agree on the derivative at that point. So that's totally fine. They satisfy both conditions of smoothness and continuity. Cool, that's fine. We turn through here, that's x squared. We know that's differentiable, so that's fine. So that's all fine. What about this other transition point? Okie dokie. Let's go green. Okay, this thing derives to 2. So when x is 1, because that's our transition point, the derivative is 2. Okay? What about when this thing is +1? Well, +1 into that will also be 2. 1, 2, and 1, 2. Great, the derivatives agree, so that's great. So they're at least smooth. Are they continuous? Well, let's put them in. So this guy, we put in 1. 1 into that gives us 1 back. And blue. 1 into this gives us 1 back as well. So they agree on the position, so they are continuous. And they agree on the derivatives, so they are smooth. They are continuous and smooth, so it makes sense to have some sort of derivative here. So that's fine. And we know that 2x minus 1 is differentiable, so everything's fine up that way. -2x minus 1 is also differentiable, and x squared is also differentiable. So even though this was a fiddly complicated thing that had a whole lot of hybrid in it, it's differentiable everywhere on this. On the transition between purple and blue, it's differentiable everywhere on blue. It's differentiable on the transition between blue and green, and it's differentiable on green. That's everything. So it's differentiable everywhere, even though it looked like it might not be. But very commonly with hybrids, they're not, but so long as the transitions are all good and the actual functions are fine, you can differentiate it anyway. Beautiful. So that's everything. It's a pretty short one. There's not that many questions in there either. Do email me if you've got any troubles. With this worksheet, again, it doesn't have to be absolutely perfect. It's just trying to get going up at the right time, going down at the right time, and crossing the x-axis at the right time. Cool. Email me if you've got any troubles. Best of luck. Cheerio.